Triángulo. I live in Berlin, Germany, but I am from Colombia, South America. That's why the accent. You can find me on GitHub, LinkedIn, Twitter, all that stuff. I work mainly at Forto, a company in San Francisco, doing machine learning for the customer experience area. I also help other companies with external consultancy and things like that. And I have built some open source packages. Some of you know about FastAPI. The other things are not that known. So yeah. Cool. So first, let's start talking about async and await and concurrency and like what is the whole deal with this. Probably many of you already know. You're gonna get bored. For the rest of you, it might be interesting. So the idea is Python is a very fast programming language when you compare it to the network. So the network is very slow. Let's say that you have some Python backend that is running on the CPU and is running and executing code, and then you have a client that is communicating with that backend. Then the client will send a request, and the request will go very slowly through the network. And then the code in the backend is going to be waiting for that request. Then it's going to receive the request, process it very fast, because Python is very fast when compared to the network. And then it's going to return the response. And then the response is going to go very slowly back to the client. So there's a lot of waiting, a lot of just waiting for things to happen, instead of being executing and using the CPU. So, okay, let's try to improve things there. If that's how the network works, why don't we have multiple clients and then all of the clients handled by the same Python backend? So that's a very nice idea, and it's a very interesting idea. But the thing is that if we implement it in the simplest way, then we will end up with something like this. It's just a line of clients where, I don't know, for this guy over here to pay for his milk, he has to wait for the other guy to pay for his drink or toilet paper, I don't know. And before he can even put the things on the belt, the other guy has to go first and probably even pay before he can even start saying like, this is what I want to pay. And he cannot just like go and move around the store. He just has to be waiting in line for his turn. So he has to wait in line for the people in front of him and the people in front of those people, for everyone just waiting there. So that's what we will end up if we implemented the thing in the simplest way. It will look something like this. You will have a client that will send a request very slowly. You will get to the backend. Then the response will come back very slowly, and all the other clients will be waiting for the first client to finish. So there's a lot of waiting. And again, we have Python and the code that is running very fast in the backend, just waiting for the network. So how can we improve it? Well, this is how your API app will end up looking like, just because it's just waiting. So now let's improve that, and let's put a waiter. Let's imagine that we are in a restaurant and we have a waiter that goes to the tables. So the waiter goes to the table to one client and says like, hey, what do you want? Here's the menu, and then the client will take a while checking out the menu, and then the waiter can go to the next client instead of waiting for the first client to finish deciding what he wants. So if we put the system like this, it will look something like this. This is all in Python. You have your code here, and the code will be like kind of a kitchen, preparing each of the dishes and the plates. And then having this new thing that we have in Python, this async and await, this will be kind of like having this waiter in the restaurant. And this async and await stuff will be what goes to the first client and say like, hey, here's the menu. What do you want to order? Maybe this is my sister that is very slow to decide what she wants. So the waiter can go to the next one and ask, hey, what do you want? Here's the menu. And then the waiter can go and ask to the next client, what do you want? Maybe at that point, finally, my sister decided that she wants some chicken. So my sister can say, hey, I want some chicken. And then the waiter can say, okay, here's this client wants some chicken, and then the network will take a while coming here. But then while the request and the order comes back here and goes to the kitchen, the waiter can continue asking the next client, and so on and so forth. So the thing is that you don't have to wait for each one of the operations with one client to finish before starting processing the other ones. And the point here is that the kitchen will always be cooking. That is the whole point, that the CPU will always be used, so that you're not wasting CPU. So you can have Python be as fast as Python can be, instead of just waiting for the network. That is the whole point. That is the whole thing that async and await gives us. That is the whole benefit, and that is why we will get like better performance in terms of concurrency and throughput and all that stuff. Now, performance in terms of concurrency and throughput, like what? So many terms. So let's try to see a little bit what all those terms mean. So first, we used to say about parallel stuff and concurrent stuff, and like it's not very necessarily not very obvious what each one of those means. They are kind of related, but they are a little bit different. So parallel means two things at the same time. So imagine that we are, you and me, we are cooking together. So I'm cutting onions and you are cutting tomatoes on the side. We are both doing something at the same time. Exactly at the same time. I'm cutting and you are cutting things. We are chopping, I'm chopping onions and you're chopping tomatoes. So that's in parallel. Concurrent means during the same period of time, not exactly not exactly at the same moment, but during the same period of time. So imagine that I'm cooking by myself, and then I have the tomatoes and the onions, and I put them on the pan. And while that thing is being cooked and is being fried or whatever, I can go and scramble some eggs. I could just be looking at the pan and just like I'm just cooking onions and tomatoes and just waiting there. But instead of just waiting for something that doesn't require my work immediately, I can just like leave that there in the stove, and I can go and scramble some eggs at the same time, or actually during the same period of time. So I will be cooking onions and tomatoes while concurrently scrambling eggs. And then I can put the eggs, and then I can continue. The thing is that I wouldn't have to be waiting, just doing nothing. That is the whole point, to not be waiting, doing nothing. So that's what concurrency will mean. Normally, concurrency doesn't mean that you are never doing things at the same time. So the term doesn't necessarily imply that, but in most of the cases, it means that you are just taking turns to do different things during the same period of time. That's what async and await and the waiter at the restaurant will give us. Now, another like another idea is like, when would you want to use parallelism and when would you want to use concurrency? So the thing is, if there's a lot of waiting, for example, you have a lot of users, you have a lot of clients, and there's like the network, and you have to wait for the clients to reply back, or you have to wait for the database to process stuff to give that back to you, or you have external APIs, or you have to read from disk or things like that. That's a lot of waiting. In those cases, something that enables you to use concurrency will help a lot to improve the performance of the whole thing, just because you are not wasting CPU. You're not wasting time not computing anything. You can be computing all the time. Now, parallelism. In Python, you normally will do parallelism by having multiple processes running at the same time. Or if you're using extensions or something in NumPy underneath that can take advantage of other things, or that can use GPUs or whatever, that will be computing things at the same time. But for those cases, it's for doing things that require multiple small tasks that are normally very similar, or the same task that you can do at the same time together. So for example, image processing or machine learning or things like that. So it's not that concurrency is better than parallelism or parallelism better than concurrency or something like that. It's just different terms and that have different tools and different things that are useful for their own use cases. Now the other thing is that we talk about performance and speed, and like it's very nice to talk about a simple word and just say like, I want the best performance, but what is performance? It's not very obvious, and it depends on the specific use case and the specific things that you're trying to achieve. So it's probably better to talk about throughput or latency, but then throughput, what is that? That sounds so academic. So throughput is just the amount of items passing through a system. So you can think of requests per second, or like the amount of clients that you can handle per second with a single server or something like that. In this case, when you need throughput, when you need to have 10,000 of users at the same time, then the tools that enable concurrency will help you. But when what you need is latency, latency means how long each individual item takes. So you start something, and when does that finish? It's very different than having 1,000 people starting something and when everyone is finished in the end. Because if I start something and it takes 5 seconds, but at the same time, another 10,000 people start the same thing, and it just takes 5 seconds for everyone, then I have very high throughput, sort of, because like I'm being able to handle 10,000 users in just 5 seconds. But if what I care is about each individual item, then that's the latency, the thing that the amount of time it takes for one single thing to happen. In that case, you might need to do some other ideas to have a better code optimization, like using NumPy, using GPUs, using MyPyC, Python, Rust, or a bunch of other tricks just to optimize each execution of the code. Because in those cases, like you are needing the CPU to execute fast. You're not needing to avoid waiting and just like use the CPU at maximum. You're just wanting to optimize each one of the little pieces. So in those cases, concurrency is not the thing that you need. In those cases, you need to optimize the code at some other level. This is just to try to clarify a little bit like the things and the terms that we talk about. But the rest of the talk is just about concurrency. So for the other things, you can remember the past talks that we have been seeing. Cool. So this is a lot of boring terms. So let's switch to something more interesting. So let's talk about using async. So this is how async works. Probably many of you already know, but for those that don't, this is how it is. So you have only a couple of rules. The first one is that you can only use await inside of async functions. This await over here. This is the point where you tell the waiter in the restaurant, hey, this might take a while. So it's like, give the order to the client and then await, because the client is going to take a while to decide what the client wants. So you will put an await there. This is what tells the waiter, hey, you can go and do other stuff, like attend, serve other clients or do something else. Now, await can only be used inside of async functions. So we have to define this function using async. This is what tells this whole thing that inside of that we need the waiter. We need to be able to wait for some stuff internally. Now, the other rule is that to call an async function, you need to use await in front of it. So this means that this is an async function, and to be able to call it, to be able to get the information, the return value, we need to await that. So let's actually go and check this do work function. So do work is also an async function, and it's doing some stuff internally here, and it's doing some work. And then to be able to call this function, we have to await for that function to finish. So that's the whole thing. That's like the main two rules that you have about async and await. You just have to use async for the functions, and then to await for some stuff. Then to call those functions, you need to use await. Now, at this point, you might be thinking, so how do I call the first one? Because like, if I can only have await inside of async, but then async can only be called with await, like how do you do that? And the trick is you don't. You use another library to call that function for you, and that other library in this case is any.io. And what this library will do is that this library will go and call the main function, which is an async function, and it will do all the stuff that it has to do. It will set up the event loop and all those fancy terms, all the things that it needs to do to be able to have the waiter that is gonna wait for all those things and call the async functions and do those things. This is how you run an async program by yourself. Now, yeah, so you just don't have to await the function yourself. You just make a library, do it. It's better explained like that, right? Anyway, so now a simple example of something that you could see in the real world, I guess. So with FastAPI underneath, for those that don't know, FastAPI is an API framework, but underneath it's async. It's an async framework. So it's already doing all this stuff underneath so that you can have async functions, and they will be, you can just like await them, all that stuff. So you can just create a function that will receive requests that go to this URL, to /recipes/ name is a parameter, and the name will be read here. And in this case, we are using HTTPX to do HTTP requests. So HTTPX is the next generation library for working with HTTP, the HTTP client. it's like all the interface is made to be compatible with requests, and it supports both async and non-async. So you can use the same library for everything. So now what we do here is that we do async with. If you're not familiar with the normal with statements, what it normally does is that it does some setup, something internally, and whenever this block finishes, so whenever the indentation finishes, it will do some stuff to close that thing, to finish that up. Now, async with is the same, but using await. So the closing step, can you also use await stuff? So this will be the equivalent of having an await here at the end, saying like, hey, await for this client to finish and to close. So just close this thing and finish that thing. This is what this async with does. The point is, you use this client with async with, and then inside of here, and what it will do at the end is it will just close the connection, sounds like finish all the resources and all the stuff, so to clear up everything. But then you can just await this client.get to get the request. This means that this endpoint, or this path operation in terms of fast API, this thing that handles requests, will be able to handle a lot of requests and a lot of users, because it's just communicating with another API, but the communication with the other API is also not just hanging there waiting, doing nothing. While it is waiting for the other API to reply back, it's going to be able to handle other clients and do other things. So that's how you will do it probably in real life. In this case, because Fast API will take care of calling this function for you, you don't have to call it yourself. So in many cases, this is how you will end up using async and await, just using async and using await internally. And of course, then you can go to the documentation side, and it just works normally, and you can just send requests, and it will just like send you the requests, the responses normally. So you can just like interact with the Fast API as normally. Now, in the case of Fast API, and this is particularly Fast API and HTTPX, both are compatible with both async and non-async functions. If you define a non-async function, it will do the smart thing underneath that is running it on a thread pool, but I'll tell you a little bit about it later. And then HTTPX.get is also compatible with just calling it directly and not using async. So the thing is, you could have a Fast API application that underneath is all async, but then you can have code that is blocking, and then just use blocking function, normal def functions everywhere, and just not use async anywhere, and just use like the normal code that you already have. And then you can migrate to async and await only the things that need to improve performance and things like that. Cool. So in the case of Fast API and HTTPX and other libraries, you can use async and await or not. So you can use whatever you want. Now, let's talk about this concurrency thing, but in your code. So how do you achieve this concurrency stuff? How do you make something be run during the same period of time? So let's take the first example. This first obvious thing that we could do with the things that we have said up to now. So we have a function async, and inside of that we are using a wait. But the thing is that we have a wait one after the other. So what the Python waiter is going to do is it's going to go to the first table, and then it's going to await there. It's going to send, give the menu to the client, and then it's going to see, what else do I have to do? I don't have to do anything else. We only have this one client. What is the next step? Just to wait. So it's going to wait there. Then it's going to do the next step, and then it's going to do the next step. So this one won't happen until this one is finished. So this is not concurrent. If you are running a Fast API server, then or something like that, something that is already having some other way to handle some type of concurrency, then maybe at this point it will be able to handle another client, but something else in another part of the code, not here. So this is actually not concurrent. So we are using async and we are using await, but we are calling the function sequentially. So this is actually not going to run concurrently. Those functions are not going to run during the same period of time. So how do we do that? Then we can use, I have been showing you AnyIO. Now I'm going to show you Async, which is a little library that I built on top of AnyIO. And I'm going to show you a little couple of features of why I'm showing you this. So we import async and then we use, again, one of these async with blocks. And we say async.create task group. This task group, this comes directly from AnyIO. So all the work is actually done by AnyIO internally. And I'll show you a little bit what is this async AnyIO and what's all that stuff. But the point is, this async with will have an implicit, will have an implicit await here at the end. And the await here at the end will tell Python, hey, wait for everything to finish before you continue running whatever you have to run. Now, this creates a task group, and then with this task group, we can say, hey, I want to soonify this function, and to soonify will mean create me a function that will be called soon. So we say soonify, and then we can pass the parameters that we will pass to the normal function. We pass all of this. Look that we don't have any await anywhere here. We only have the async with. So now the task group is going to take care of running all these three functions concurrently, so during the same period of time. Whenever it has to wait for something inside of one of those functions, it's just going to jump to the next one, and then it's just going to jump to the next one, and it's just going to just finish in a lot less time. How do you say that? Well, anyway, it's going to finish faster than if you were just waiting for each one of those sequentially. If and only if the functions internally have something that they have to await for. So if they're waiting for the database, they're waiting to read a file, they're waiting to communicate with some external API, then you're going to be able to do those communications during the same period of time. For example, you can communicate to Stripe and to the database and to the logs and do that concurrently. Instead of waiting for one, then for the next, and then for the next. You can just do that concurrently and then finish faster. So in this case, that single request can have better, let's say that that's an API call. In this case, that will also improve latency, just because you are avoiding waiting internally for this single section of the code. Now, why is this, actually, let me go back. Why is this design of this soonify and then passing the arguments afterwards? So one option will be to pass the arguments here internally, but then because of the way the language works, you wouldn't have autocompletion and you wouldn't have inline errors. But Async uses a bunch of typing tricks so that if you do this, then you will have all the checks in this part. For example, it will be able to tell you that you are missing the parameter name. So notice that we are not calling the function directly. We are sending it to something that will call it for us, but we still get the checks telling us, hey, you are not calling this properly, you need to pass a parameter name. And we also get autocompletion for the parameters of this function. So we don't have to blindly guess or remember or figure out how to pass the parameters. We have the same autocompletion that we will have if we were calling the function directly. That is the whole point of this design of this soonify thing. And that way, now you can have multiple tasks that are running, and then when they have to wait, they can just point at the other task, and then the thing in Python that is executing that will be able to execute each one of those different paths. Now, let's say that you need to get the value of those functions. You don't need to just make them run, you need to extract the value from them. So in this case, we have this is the function. This is this await any.io.sleep. This is the equivalent of time.sleep. So this is the equivalent of just waiting there doing nothing to simulate that this is actually calling an API or talking to the database or something. But in this case, because it uses await, it's not consuming the CPU doing nothing, because that's what time.sleep does. It just tells the CPU, hey, hang in there, just look at me, stare at me intensely, let's do a stare contest, do nothing, and now you can continue. And that's when you waste CPU. But in this case, it's telling it, hey, go and do something else for 1 second and then come back because I'm going to be ready. This is what it does. It's just to simulate an actual communication with async and await. And this is just returning a value, but we need to get access to this value in this case. So in that case, we can, the result of calling this soonify, blah, 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 and then calling the thing with the arguments, this is going to return something here. When we execute this value, this is a soon value, this is still doesn't have the value of the return of the async function, because this function is still not called. The task group is going to call all of these functions concurrently by the end of this block. But we can have this soon value here, and then we can use it later outside of this async block. So look at this. This is the indentation back to normal. So we are outside of the block. Now we can use each one of these variables. So these variables are soon values, and then when we are outside of the async block, we can use the dot value attribute, and that's going to have the value that was returned by the async function. So we can just get the values back there. Now, because this uses a bunch of tricks in type annotations and all the stuff, we're going to have autocompletion and inline errors for the value, and this value is going to extract the type information from, in terms of the editor. The editor is going to know what is the type of the value that is returned by your function. So if this was returning an integer, then we will have autocompletion here for an integer. Or if it was a custom class of some type, then we will have autocompletion here for that custom class. So just in case you didn't know, the type annotations are what allows us to have autocompletion and inline errors. The academical terms is static analysis. That sounds very fancy, but it's not very easy to understand. The point of type annotations is having autocompletion and inline errors. In this case, because async error uses a bunch of autocompletion, a bunch of typing internally, then you can have this autocompletion and inline errors. And of course, you can also have like the inline errors. It will tell you, hey, you cannot sum a string with a number. So that is also the other reason why you could want to try async because it allows you to extract the values directly. And now, actually, let me go back for a second. So we are getting these values, we are putting it in this variable data, and then we are returning the data here. The thing is, because it's using all the type information, also from each one of the functions that you're running, then whenever you call this function that we defined here, let's go back. This function get data, this is returning the data. Whenever you call that function get data here, because it has all the typing information, even from the functions, the async functions that you defined, when you return the data, the editor is going to know what is the type of this data. So it's going to know that it's a list of strings. So then you can get this data and you can iterate for each message in data, and you will still have autocompletion and inline errors for each one of the return values of your concurrent functions. So you can have like all this safety and all this consistency and like confidence that your bug is a little bit less full of bugs. So now you're doing some concurrent code with just a little bit of salt, async salt. Now let's talk about the important part, probably what you came for. Well, actually you didn't have any other option, so yeah. Which is using blocking sync code inside of async code. So the thing is, when you run code that is blocking, and blocking means one of those things that makes the CPU just wait there and do nothing and stare at you without doing anything. That's blocking code. That is just normal functions, def functions, but that have something that will just take a while and not do anything during that time. That won't allow Python to continue executing, that will just like hold it there. Like time.sleep, or waiting for a connection to the database, or using requests.get, something like that. That doesn't have a wait. So when you do something like that, this is gonna block Python, and it's gonna make it wait there. If you put code like this inside of async, then it's gonna make the waiter this and just like call it like here. You cannot put a wait here because this is not an async function. So you just will have just to call it like this. But if you call it like this, then this will be the equivalent of having a restaurant with a waiter and having the waiter go to one table and ask, here is the menu, and then just stare at you while you look at the menu and just look intensely, waiting for you to say what you want. So that will not be efficient. Instead of going to other tables and asking other and doing other things, or like, I don't know, cleaning tables or something, we'll be just waiting there, doing nothing. So that wouldn't be efficient. You have a waiter, but you're not using it. And it's also just gonna block all the other orders, all the other tables. So this is something that you shouldn't do. If you have heard that, oh, if you use async and await, then everything has to be async and await and everything has to be compatible and all that stuff, this is what they refer to. This is what they talk about. Now the thing is that you can actually, there's a way to mix them. And that's what I'm gonna show you. But first, yeah, just don't block sync code, don't run sync code in async code, because there's no await. You cannot call await internally. You can laugh or not. Okay, so this is not something that will break Python. And this is probably the most dangerous thing, that Python will not break. You won't have an error, you won't have a syntax error, you won't have something that explodes. It's just gonna be slow. And that is the part that is most problematic, that because Python normally tells you, hey, this is broken, fix it right away. It's not like JavaScript that says like, yeah, well, let's continue, let's see what happens. Right? Python tells you right away. But in this case, because it doesn't have a way to know like, oh, this can be very problematic because it doesn't know yet, then it's just gonna try to run, it's gonna execute, and it's just gonna degrade performance. So there are some kind of performance rules that you should avoid, which is do not call blocking sync code. Sync means def. Functions called that are def, that are not async def, just def. That is sync code. So it's just synchronous. It's just not being awaitable. And blocking is one of those functions that will end up waiting for something. So blocking will be like time.sleep, or there are like some low-level parts of Python that do things that are end up blocking, like communicating with sockets or things like that. But then you normally don't use that directly. You normally use libraries that do that internally. So you will use a driver for the database, or Elasticsearch, or requests, or something to, or you might use open to open a file, and that is blocking. And that's probably one of the few things that you will use directly that is blocking. But the thing is that you should not use blocking sync code in async code directly. So if you have an async function, don't call something that will block inside of that async function. Just don't do that. You just have to convert it to something that is awaitable. You need a way to be able to put await in front of that. And that way, you will be able to run it. And the way to make it awaitable is to run it on another thread, to run it on a worker thread. That way, the CPU will be able to do its thread magic thing to jump back and forth and check, is it done? Not yet. Is it done? Not yet. Is it done? Not yet. And it's not as performant as using async and await, but it's going to be able to do the thing that, and like give you the best performance that you could get if you were not using async and await. So you're going to be able to just like have the best that you can have with async and await, while still having the rest of the things that you are normally having. Now, what is blocking sync code? I have been talking about blocking sync code. I'm like, okay, how do you know what not to run? So it's normally things that don't use async first. They also require waiting for something, so waiting for a database, or waiting for another API, or waiting for a file to be read from the system, or that interacts with something outside of your code and variables. So if you have some code that reads another variable in your code, that's not going to be blocking. It's just in memory, it's just checking the RAM. But if it's interacting with the network, with external APIs, with external databases, with files on disk, many things like that, then that's probably going to be blocking in some way, unless it is using async. But in that case, you're already using await, so you know that this is async code. So these things, anything that works like this, are the things that you shouldn't call directly. It might be a function that is called, and that function might have some decorator or something that will cache the results in Redis or something like that, and you might not necessarily know that it's actually blocking, but it will be blocking if it has that communication with Redis or with anything else. So anything, the first thing is like any function def could be blocking if it has something internally. If you don't know, then like you will have to check. But if you are using a library that communicates with something externally, and it doesn't use await, then you can be pretty sure that it's going to be blocking. The other thing that could block in a strange way is something that consumes a lot of CPU for a long time. It's actually not communicating with something outside. It's actually not something that is not using the CPU, so it's just going to be using the CPU. But if you have, like, I don't know, you have a web API, and you try to run, to train a machine learning model in the thing that handles a request, then that's going to just take a while, and it's not going to return the response to that request, and it's going to hold the other requests at the same time. So it's just going to hold everything until that thing is done, just because it's consuming CPU. So, but like this will be smaller cases of something like this, and you will probably know which of those are already, because like that's already like very heavy computation that you're doing somewhere. So it's not something that you should be like extremely scared of, because you will normally already know that this part is very heavy computation. But these are the things that you should be looking out for. Now, how do you run blocking sync code in async? So from Asyncer, you can import this asyncify thing, similar to the Sunify thing that I was showing you. Then you can have let's say we have this async function, and we have this blocking function, this blocking synchronous function. And then you can just do asyncify and pass the function that you need to make asyncable, that you need to make awaitable. So this will be the equivalent of telling, hey, I want this function to be kind of async, the equivalent, the best equivalent of an async function. And then you can pass the parameters. And that's it. This is going to run this on a thread worker, on a worker thread, and it's going to just wait for the result, and it's going to give it back to you. So now you're going to have the message here, and you're going to be able to just, this is how you're just running blocking code inside of async. And this way, this won't be blocking all the rest of the async code. That's it. Like all the stuff about threads and all that, that's how it works internally. But what you need to do to be able to run synchronous code, blocking synchronous code inside of async is just this. There are other approaches to achieve the same. Async IO has its own way to run something on a thread worker. Any IO has a very similar thing. This is just syntax sugar on top of any IO, in fact. But the thing is that this will make it very easy to mix sync and async code. Now again, this design of passing the function to this thing and then calling the result of that is also because you can have inline errors automatically. MyPy will detect it, the editor will detect it, and you will also have auto-completion for the things that you need to use in that function. That way you can have like the same kind of interaction and the same user experience, developer experience that you will have if you were calling a normal function, but now you can mix async and blocking code. So yeah, that's pretty much it. Now you know async full. Now, how do you call async in blocking sync code in async code? So let's go back a bit. Let's say that you have an async function and you need to call a blocking function inside of that, just like what we did. But now you need that blocking function to internally call an async function. So let's check the code. So we have asyncify. There's also another syncify. Such imagination, right? Cool. So we have the same blocking function that we had before, but now this blocking function needs to be able, and this blocking function, let's go to the main function first. So we are just calling an async function, and this async function is running a blocking function. This is gonna do the thing on the thread worker, all that stuff, to allow you to call it directly, and then you're gonna just receive the message here. Cool. So this part is the same that we just saw. Now let's check this function. This is do sync work. So this is blocking synchronous code. This is just gonna wait there for 1 second, doing nothing, just holding the CPU, doing nothing. And then this also needs to call async code from here. So what we do is that we just do the same thing. We just make the async function, we syncify it so that we don't have to use await. So now this is the equivalent of a synchronous function. And then we can just pass the parameters, and notice that we are not using await because we cannot use await inside of a function that doesn't use async here. And then this is going to be an async function, that is this one over here, and this is just the other thing that is doing the work. Now, the way that this works is that we start, whenever you do any IO.run, or like whatever is calling your main async function, whatever is calling this, that's gonna start in the main thread. And this main thread is the thing that is running what is called the event loop. So the thing that has the awaiter and all that stuff. Now, when you go to this point, this is jumping from the main thread to a worker thread. And this worker thread is what is gonna execute the work of the synchronous function. When this worker thread is done, it's gonna take the return value and the result of that, and it's gonna send it back to your code on the main thread. But now, before it does that, this has this syncify thing here. And what this is gonna do is that you are here on the main thread. So let's start again. You're here on the main thread. Then this is asyncify is gonna make you jump to the worker thread, or it's gonna make Python jump to the worker thread. Then the worker thread has some code that needs to run asynchronously. So that is gonna jump back to the main thread, and it's gonna send that task to the async event loop and all the stuff and the fancy terms, it's just going to send it back to the place where async code can be executed. Then that is going to execute, it's going to get the result, and then it's going to send the result back to the worker thread. And now the worker thread has this value here, this message here, that came from the main thread that ran this thing. And now when this is done, this is going to return the message, and that is going to jump back to the main thread that is running all the async code. So it's just, you can use asyncify and syncify to go back and forth from the main thread and from the worker thread, and that's the way that you can combine async and blocking code, and like even go internally, go deep using async and await and all that stuff. Now again, the design of this syncify thing uses the same idea, so you can have inline errors and autocompletion and all the stuff. And of course, the result here, the result of message, this will have autocompletion and inline errors on all the things for the return value of this function and all those things. So like all the types are there in place using like, actually even like very recent improvements and standards and things in the type annotation world in Python, so that you can have like all these features in this very simple and nice way. Now, if you feel that this async and syncing, async and all that stuff is a little bit confusing, you're not alone. I am confused as well, because this is a little bit mind-bending. But when you think that you are just jumping back and forth from two places, from the main thread and the worker thread, and maybe the worker thread has something that sends you back there and then back and forth, and like you're going down in levels, but each one of those levels is only in two possible places, in the main thread or a worker thread. Then that might help make it a little bit easier to understand conceptually. Either way, you can just use asyncify and syncify, and like it will do the thing underneath. Now, you can actually use async in blocking sync code, and you can have it work in a dual way. So up to now, I have been showing you how to run code that you start from a main function that is async function. What happens if you need to be able to run the whole thing, your whole code base, in async or in blocking code? So you have, let's say that you have a async main function that you will run with any IO.run main, so the thing that does all the async stuff, but you also need to be able to have all that code be run from a normal synchronous function. An example of how you might want or need to do something like this is if you have a Flask application and you have a FastAPI application, both sharing code, both sharing utilities, or you are like, I don't know, migrating, or like you're trying to migrate to FastAPI, or you got really tired of FastAPI and you're going back to Flask or something like that. In that case, you will need to be able to run like all your code base in both sync and async, and you will need those places that switch back and forth to be able to be compatible with both. In those cases that you need to do that, you need dosync work, and this dosync work to be able to call async code without exploding. The thing is, when you call syncify, when you call something that is trying to send async work to the main thread, but there's actually no main thread, there's actually no async stuff running that, by default Python will just explode. In those cases, you can use syncify has this parameter raise sync error equals false. This means that if you try to do, hey, I need to run this async function in the main thread that is doing like all the async stuff, I need to run that there. But if there's no main thread, because this is already in the main thread, because you are not working with an async program, what this will do is that it will start the event loop and all the stuff and do everything so that you can run this function here in this line directly. Of course, that's going to be computationally more expensive than if you had already like an async program to begin with, so that you can just run this. But the thing is that having this, then this line will work in both cases, when you have a mainly async program or a mainly blocking program, and it won't explode, which is what you might want in that case. It's optional because this will have a performance penalty because you are starting the whole thing that you are hiring the waiter for the restaurant, and at this point you are firing the waiter for the restaurant. So It's a whole admin process that you don't want to do in every place. But if you need to be able to run some async code, if you need to be able, for example, if you need to be able to do something concurrently using async, and you need that to work. You need to be able to use async and await, because those are very nice constructs and like all these ideas. But your code is still mainly synchronous. Then you can just use this and just call the function that will do like all the async stuff, and then just continue with your normal synchronous code. So in that case, you can use Syncify to use mainly async code or mainly synchronous code. Now, about libraries and like what to use, and like there's a lot of like, okay, async IO and any IO, and this thing that I'm showing you, async and trio, and like all the stuff, like how does all this work? What is the relationship? So all of them use async and await. So if you just use async and await, all of them will be the same. All of them will work the same. If you need to yourself start an async program, then you need to use one of these libraries. Or if you need to yourself call things concurrently, then you're going to need one of these programs. Now, async IO is the thing that is internally in Python. So when you have Python, you already have async IO. So this is the thing that has been there, well, not forever, but since it was there. And there's this other library called Trio, which is an alternative library, an alternative implementation. There is async and await that has a bunch of nice features that allow you to handle concurrency in a more structured way. So they have these task groups things, and these task groups, and like the ideas related to that, are called structured concurrency. But the thing is that the main point is that when you have this async block, you know that everything inside is going to be finished by the point that block is finished. That is the main point, and that is the main idea of this structure, concurrency, and all the stuff. That way you won't have to be debugging down the line why something happened, why something broke in some other place, because you know that if something is going to break, it's going to break inside of that with block, not afterwards at some other point. That's kind of the main idea with this. Now, so there's async IO and there's Trio. There are libraries that are built on top of async IO, and there are some libraries built on top of Trio. Not that many on top of Trio, much more on top of async IO. But the ones and the others are not compatible with each other. So you need to choose one. You will normally choose async IO because most of the libraries are for async IO, and because there are some things that improve, that do optimizations for performance and things like that for async IO. But you might want to be able to use these structures. So if you are using one of these, you have to choose one or the other. But then there's any IO, which is just a library on top of each one of the two. It can use one or the other, and any IO gives you the same ideas that were defined in Trio. So you can use the same ideas, use the task groups, and use all the stuff and the structure concurrency and all those things with any IO, and that way you can switch from async IO or from Trio, whatever you want. So if you have to choose what to use, then choose any IO, because it's just compatible with both, and you're gonna have like the most compatibility possible. You have the structure concurrency, task groups, and all the stuff. If you're feeling experimental, you can try Asyncer, which is the thing that I was just showing you, which is just any IO. It's very tiny. You can install it, and you can just copy the code and put it in your code base, and just check it. It's just any IO with the type annotations, so you can have auto completion, inline errors, mypy checks, like all the type safety and all that stuff. Trio is if you want to see like the like, I don't know, the core ideas that started all this stuff with structure concurrency and all those things, and if you want to work with that directly, it will be Trio. Async IO, if you cannot install anything in your environment, you just have to work with Python directly, then it will be Async IO. Async IO is the thing that comes with Python. And the next versions of Async IO will also have task groups, and they actually just approved some change in the language of Python itself to improve some of these things, which is called the exception groups. One of the things about this structure concurrency is that if some of the concurrent functions has an exception, like how do you handle it? Do you send the exception to the other concurrent functions, or like do you wait for all the exceptions, or like how do you handle that? So the way that it was done in Trio and with any IO is that you will have a group of exceptions. So it's an exception that internally has a group of exceptions, so you can get all the exceptions from all the concurrent functions. But that's still like not super convenient because you don't have access to each one of the exceptions. You have to inspect that group of exceptions to then extract the others and things like that. They are adding things to the, well, they added things to the language so that you can extract exception groups and have like all the exceptions together and like extract them and like log them and do whatever you want. So that already came to Python. That's gonna be used in all these things. So in the end, we're gonna have like all these tools and ideas in like all the places. But meanwhile, you can probably just use any IO. And yeah, nobody expects the end of the talk, but that's what I have for you. Thank you very much. I don't know if you have questions.